organizers from letting a PhD student talk among such famous people. And what I'll talk about is the geometry of the Brownian curve as seen as a conformally invariant object. And in particular, I will describe some subsets of it which are invariant under the conformal maps. And in particular, derived some Hausdorff dimensions of such subsets related to exponents such as those that were calculated by Loewner, Schramm, and Werner. So I start with a brief review of what is basically Loewner's work as the relation between the non-intersection and non-disconnection exponents with some related subset of the curve. I start with the psi of 1, 1 exponent. I will use the notation of the former papers by Loewner and Werner without Schramm. I recall you that if you consider two planar Brownian paths started from radius 1 and killed at radius r, and you look at PR is the probability of non-intersection up to radius r. Then it was proved that this behaves like r to the minus something like psi of 1, 1, 1, and 1 meaning one family of one Brownian path and one family of another Brownian path, meaning the families are quite trivial in this case. And natural question is, what is the related subset of the Brownian curve? To do that, you can rescale this by dividing by r. And what you find out is, if you take a Brownian curve, and you take one point bt on the curve, and you consider the future from bt plus, and the past up to time bt, these are two independent Brownian motions starting from bt. So if you consider the path from the distance epsilon from bt, then you have the probability that those parts don't intersect. From this formula, this is epsilon to the psi of 1, 1. And hence, I will come back to the hence later, but this leads to the fact that if you let epsilon tend to 0 and take the intersection of all those sets such as the two parts don't intersect, you get a set of points named cut points, the definition of which is the set of bt such that the whole path b up to time 1, say, minus bt is not connected. Such points are called cut points, and this says that almost surely the Hausdorff dimension of cut points is equal to 2 minus psi of 1, 1. Then by the later papers by Loewner with Schramm, they derived the value of psi 1, 1, which is the famous 5 quarters. So this is 3/4. I will take a little less time for the following ones. Eta of 1 is the non-disconnection exponent. The related event is the following. This one uses only one path. And you consider the probability that this path from radius 1 to radius r lets in a space between 0 and infinity such that there is a continuous path escaping from 0 to infinity. This is called disconnection. And this also appears with a probability which is r to the minus eta of 1 for some value of eta, which turned out to be 1/4. And if you do the same transformation here, you describe points such that bt is on the outer boundary of the path up to time t. Such points Loewner called the pioneer points. And the same result holds here. The dimension of pioneer points is 2 minus eta of 1, which is dimension of pioneer points is 7/4, which is closely related to what I think it was Venlein told in his tutorial about SLE, which is the dimension of the trace of SLE6 is the same 7/4. The object is not the same, but it's quite close. Last thing.
What is the topology of this set of pioneer points?
Of pioneer points, it is connected, but basically, if you grow the SLE, you make bubbles like that. If you grow the pioneer points, say from a disk, you can do a bubble here, and then spend some time in the interior, and then start out at another point. So, as the dynamic object is much more complicated.
Right, but seen as a trace, is that a kind of? It's not a simple curve.
Definitely not.
Is that branch or not? Or is that just?
You mean, is it generated by the path?
Yeah.
This I don't know for sure. I won't answer. I'm not quite sure of the reason of the answer. Well, last exponent before introducing what I will be more specific about is psi of 2 lambda. The setup is the same as psi of 1, 1, but this time you have 2 paths on one side and lambda here passes on the other side. And what you obtain, let me erase this. Again, the probability that such an event is true behaves like r to the minus psi of 2 and lambda. And the related event when you rescale it is the following. These 2 paths are independent and correspond to the behavior of a curve, of a Brownian curve, around one point. The union of the 2 independent paths is the whole curve here. And this lambda corresponds to lambda passes starting at distance epsilon from bt, and you look at the probability that they escape. So this will give access to the multifractal spectrum of the outer boundary of the path, which is what Bertrand Duplantier talked about yesterday. Well, what I would like to say is some words about what is used to derive the value of the exponent, and hence to see why they are necessarily universal, which I call universal by definition. What you do to say to compute psi of lambda, 2 of lambda, first you consider the complement of the 2 paths here, and say you take the logarithm of this, and you obtain something which is here log of r, here 2 pi, and there is a crossing. One side of it is like this, the other side is like this, and the interior here that you have to avoid corresponds to the interior of the union of the 2 paths. And then what you have to compute is when you do the uniformization of this to a rectangle of length L and width pi, what you need is the exponential moments of L, that is the expectations of e to the minus lambda L, conditioned to the fact that L is finite. So basically, if you see it as a conformally invariant object, you forget everything about the precise geometry of this strip, except for the length when you uniformize it. And the natural question is it possible to say more about this strip? Say, for instance, why L behaves like something times log of R. For instance, can you say something about width of the maximal rectangle contained in this. If you try to study that, you will find out that the still exponents appear, which are the so-called cone exponents, related to the fact that saying that such a rectangle can appear means that this part has remained inside the cone, and this, the complement of the cone, is the strip you have to leave here. So there you get the so-called cone exponents, which describe quite precisely the law of the width of what remains in the complement. What I will speak about is a little variation of this consideration.
What you call the cone exponents are just pi over the angle times
Yes.
the boundary exponent.
The probability that this stays in the cone is given by pi over the angle of the cone. So the probability that there is a cone of, say, alpha behaves like r to the minus 2 pi over 2 pi minus alpha. What I will consider is another transformation of this strip by, say, a translation of one side of it. You can imagine that. How does the length of the uniformization of this behave when you move one part of it up by a fixed amount, here say alpha? This a priori can't be described using purely conformally invariant methods, because this translation is mapped by phi into something quite complicated. If you look at this strip transformed by phi, you will obtain something with a weird shape, which is not quite well described by the articles of Loewner, Schramm, and Werner. So, whoa, maybe I was too slow. What I introduce is the following. If you map this back by the exponential, is the following event: fix some set of translations which I denote by A and transform it by exponential. So fix A a part of the complex plane minus the origin, and consider the following event. Take one Brownian path and take all its images by multiplications by the elements of A. So take B union A, B union. Say one is in A. In that I will denote AB. And take another path, B2, independent of B1, and introduce PR of A is the probability that B2 intersection with AB is empty up to radius R. Then it's quite easy to see that PR behaves like R to the minus some exponent psi, which I will denote psi of A. And it's less easy but still doable, quite technical, but it's doable to prove that, in fact, the approximation by R to the minus some psi of A is true up to constants C of A and big C of A, meaning that PR of A is strongly approximated by R to the minus psi of A. To do that, we need a technical restriction, which is that A is nice, which means that if you translate it to the translations on the log space, the set of translation is bounded. So what can be done from these exponents to describe some aspect of the Brownian curve, so some aspect too of the SLE6, since we know it's the same object. Some aspects which are not quite easy to see if you see this object as the SLE, and which appear more clearly if you see it, this I skipped, if you see it as a Brownian curve. What you do is the same thing as previously. To such an event corresponds naturally a subset of the Brownian curve, which is obtained by saying that a point Bt is exceptional if the path up to Bt doesn't intersect any of the transformation of the future by the rotation and zooms and so on contained in A. This is called the A exceptional point, and it can be phrased like that. B translated by the position of Bt and the future translated by Bt and multiplied by A. This way, the intersection is empty. For instance, if you take A is only the point 1, you have changed nothing from the definition of cut point. This, for A, is only 1 point. This is exactly the same event as the one defining psi of 1, 1. Hence, this leads to cut points. One thing I will more focus in the not many minutes I have left, but on is this case. A equals C alpha. What I call C alpha is an arc of a circle with angle alpha. This leads to what I call the pivoting point, which is you can take the future of the path from time Bt and rotate it around Bt of an angle alpha, and still it doesn't hit the path of the path up to time Bt. This.
What is the exponent?
This is a good question. I will come back to it at the end of the talk. The exponent is unknown, and it is not clear how you can derive it using SLE. But the main theorem is the following. The dimension of A exceptional points is almost surely 2 minus psi of A. And if you slightly modify the definition here, meaning that there is some sort of a positive distance between the future and the past, you get strongly, I don't want to go into the precise details of it, but you get strongly exceptional points which have the same dimension. And this set of strongly exceptional points is itself invariant by the conformal maps, meaning that if you take a map of a path to another one, locally it behaves like a multiplication by a constant. And this event is clearly invariant by multiplication by a constant. So you have this way.
Could you repeat the difference between strongly exceptional and exceptional?
Yes, exceptional is this one. Strongly exceptional means that if you take basically all the Bt plus epsilon minus Bt divided by Bt minus eta minus Bt, exceptional means that this never hits A. Strongly exceptional means that the adherence of this doesn't meet A. So it's quite the same thing, but a little transformation needed to obtain a conformal invariant subset, which still has dimension 2 minus psi of A. I would like to spend at least 1 minute to say what is needed more than the exponent to derive the Hausdorff dimension. Basically, you need 2 more things, which is things that physicists don't consider often. Most times they give 1, which is the estimate of the probability, and they deduce that the dimension is 2 minus the exponent. Basically, you need 2 more arguments. This to say that if one point is in your random set, this k epsilon is an approximation of k up to scale epsilon. You need to say that this approximation is regular of some sort. This usually is given if you take the points that are epsilon close to k. This is automatic. But this one is problematic. It's a second moment estimate, which must say that what happens near 2 points of k is in some sense independent. And this is easy to see on a Brownian curve. Basically, what you have to consider on a Brownian curve to see if you are in k epsilon is something which happened between, say, radius epsilon and radius and a fixed radius, which is the distance between 2 points, which doesn't change when epsilon tends to 0. So you can separate the parts of the curve needed to say that x is in k epsilon and y is in k epsilon. And then you get this epsilon to the 2s. And this...
So in the second assumption, the condition is x is in k epsilon, right?
Yes, right. My mistake. And this is scaling to transform this into a macroscopic distance. So in a Brownian case, this is quite automatic. If 2 points are in k epsilon, then this arises. I would like to say one word about how to derive this condition to SLE in the case of SLE. In order to derive the exact dimensions for the SLE, basically this one is given by the Ito formula. This one is given because you consider the points that I have seen close to the border and to the trace. All you need is this, and basically this will be given by the restriction property, which says that what happens around 2 points which are disjoint is in a sense independent. So at least for kappa equals 6 and kappa equals 8/3, this will apply to say that the dimensions which were mentioned before are not only in expectation but have almost sure values. This is almost written down. Almost.
Still, if kappa is not equal to 8/6, you still expect the relationship to be true, right? 2
Yes, of course. And in fact, the restriction property transforms into an inequality when kappa is not one of these values. And the inequality will be in the same in the good direction. Maybe. This one is not written down at all, but for kappa smaller than 8/3 and kappa bigger than 6. Maybe. Last thing I'd like to say is that I have 30 seconds to say it. That it's important to obtain approximation up to constants for a second aspect of this, which is that the constant can be chosen uniformly if A doesn't move too much. And this plus strong approximation will give that the exponent psi is continuous as a function of A. Basically, this says that once C and big C are bounded, all you have to consider is a fixed R to get estimates for psi. And for fixed R, it's clear that this PR of R will behave continuously. Hence, what you obtain is, from continuity on the value of psi at point 1, which is the non-intersection exponent, where is my slide, is that for any sufficiently small set A, then psi of this A will be close to psi of the single point 1, hence will be strictly smaller than 2. And this gives that for any sufficiently small A, a small alpha here, the exponent is smaller than 2, hence such pivoting point almost surely exists on the curve with a positive dimension. And this can't really be proven using only SLE, because this is not a natural event if SLE is concerned. And the natural question is the maximal angle. It can be proven using direct estimation of Brownian strips that alpha max is bigger than this, which is quite small. But simulation suggests that this exponent will be close to something which is 5 pi over 2 divided by 2 pi minus alpha. So equality is almost surely false, but this is close to the real value of the exponent. So the structure looks similar to the one of the cone exponent. And this agrees with what happens when alpha equals 0, and you find the non-intersection exponent. But this also gives access to an approximation of the maximal angle, which is 3 pi over 4. And if you come back to the definition as a subset of the curve, this will say that on the Brownian motion there will be a pivoting point of angle up to 3 pi over 4 with positive dimension. Here's what it looks like. There is one part of the curve which can rotate around one point and still doesn't intersect the first part. An interesting thing which is not proven, but is that if alpha max is of order of 3 pi over 4, then it's bigger than 2 pi over 3. Hence bigger than the angle in the triangular lattice. And this could give some information about discrete percolation clusters, which can translate into events which can be stated by staying inside the discrete setup. I think I stop here. Thanks.